All right, so this is next installment in our final layer we're going to add to our dissection of chemical reactions. All right, primarily what we'll focus on with this here lecture is oxidation numbers, how to assign them, how to figure out what they are, etc. Then we'll introduce also how we can use oxidation numbers to identify when we have an oxidation and reduction scenario. Okay, so let's talk about what we mean when we say oxidation numbers. Okay, so back in our bonding unit, we talked a little bit about ionic versus covalent bonding. We talked about charges involved with ionic compounds and so on. Our oxidation numbers are similar to charges, but they're not really the same thing, because we assign oxidation numbers, for example, to our covalent compounds as well. All right, when those are not actual charges. Okay, but they're similar. And in reality, what it refers to is an excess or deficiency of electrons in bonds with other elements. So like, for example, carbon dioxide, which is not an ionic compound, right? So we're not really doing two charges here, right? We got our carbon side and our oxygen side. Our total needs to come out to an oxidation of 0 because there's no charge attached to carbon dioxide, all right? And so in this, I know oxygen's -2, right? And so I can infer, because I got two -2s, that this side needs to be +4. Now we'll talk about that little process I did right there in more detail in just a minute. I'm just trying to put this in context. Okay, so that little 2 and the +4, those are the oxidation numbers for oxygen and carbon in that scenario. All right, and so we will get to how I came up with those numbers here shortly. All right, but the purpose of this and why we're focusing in just simply on oxidation numbers right now is in order to identify a redox reaction when we see one. All right, we need to know how to do oxidation numbers, and then we also need to know oxidation numbers so we can figure out how electrons were transferred, because that's what an oxidation reduction reaction is. There's a transfer of electrons. All right, but again, it all comes down to initially being able to identify or infer your oxidation number for your individual elements. All right, so that's what we're going to primarily focus on here first. All right, so we're going to go over some rules or guidelines for assigning oxidation numbers. All right, and we're going to start by identifying the easy to assign oxidation numbers first. All right, and so essentially there's some elements that are really easy. We just see them and we know, oh, that's oxygen, it's going to be -2. Oh, that's alkali metal, those are all +1s. All right, those are our easy to assign ones. So here's our easy to assign ones. First of all, if it's elemental, all right, which means I have oxygen gas and oxygen is not bonded to something else, okay, or if I just have zinc metal or just sulfur or just fluorine gas, right? Those are always going to be 0. Okay, so they're oxidation numbers. So when it's an element by itself, right? So it's not in an aqueous solution, for example, it's just by itself, the oxidation number is going to be 0, and that's always, right? One of the few always that works in chemistry. All right, so elemental atoms are always 0. So those are easy to assign. All right, other easy to assign are ionic compounds. The oxidation number is just the charge, right? So sodium, we know that's +1. Chlorine, we know that's -1. And that's what we learned back in our ionic bonding bit, okay? Magnesium, we know that's +2. We know iodine is -1, all right? So for ionic compounds, the oxidation number is just simply the charge that you assigned when you wrote that formula, all right? So again, these are our easy to assign. Elemental atoms and ionic compounds. Now the other ones we're going to use probably most often, all right, is oxygen. So oxygen is nearly always going to be a -2. Now there are exceptions like in peroxides, etc. But for us in our high school level CP chemistry class, right, we are going to assume that oxygen is going to be a -2. So we can use that as one of our easy to assign elements. And the other one that's similar to oxygen in that it's nearly always true but not always is hydrogen. Okay, so for our in-class reactions, we see a hydrogen in a reaction, we're going to assume it's +1. All right, now again, what if it's O2 gas? Is it a plus, is it a -2? No, that's 0. Same thing with hydrogen gas. If it's hydrogen gas and it's not bonded to something else, okay, or it's not in aqueous solution, also 0. So all elemental forms, right, so if they're not bonded to something else and they're not in aqueous solution, their oxidation number is 0. Almost all other circumstances, oxygen's a -2 and hydrogen's a +1. Again, you need to learn to recognize our elemental forms, elemental, right, our ionic and oxygen and hydrogen as our easy to assign oxidation numbers, okay? Because what we're going to do then is use our easy to assign oxidation numbers to infer the not so easy ones. All right, so move on to the next page here, and we'll see how we do that. All right, so we're taking our easy to assign oxidation numbers, and we're going to use those to calculate those that are not so easy. All right, so first and foremost, if it's a neutral molecular compound, right, the oxidation numbers need to add up to a total of 0. All right, so for example, sulfur dioxide. All right, so I put in red in each of these the ones that we have to calculate. So the oxygen in this case is our easy to assign. So we know oxygen is a -2. All right, so there's no charge attached to this. So that means that my sulfur side, which I'll just call that X plus, all right, now 2 oxygens, right? So the way I'm going to write this is 2 times -2 equals 0. All right, so I'm saying my sulfur oxidation number plus my oxygen oxidation numbers need to add up to 0. All right, I know that the oxygen's a -2. All right, so I'm going to erase this just for a little bit. Okay, now I don't see an associated charge up here. That's where that 0 comes from. There's no charge attached to that molecule, so those need to add up to 0 because it's a neutral molecular compound. All right, so the 2 here comes from the fact that I have 2 oxygens. All right, the -2 is from that rule we just learned, right? Oxygen is nearly always -2, so we are making that assumption in this case. All right, so this is fairly simple. X plus 2 times -2 equals 0, so X plus -4 equals 0, X equals +4. All right, so the oxidation number for sulfur in this molecule is +4, and oxygen would be -2. So those would be my oxidation numbers for that compound. All right? All right, so let's take methane, for example. All right, so again, in black here, hydrogen is one of my easy to assign guys. All right, so there's no charge attached to that, so I'm going to take X for my unknown plus 4 times 1 equals 0. Right? So X plus 4 equals 0. X then would be a -4. So the oxidation number for carbon in this particular molecule would be -4. So it'd be a -4 on the carbon and a +1 on the hydrogen. Okay? Do one more. Manganese dioxide. All right? So here's my 2 sides of the equation. No charge attached to that, so I'm going to set it equal to 0. All right, I have 2 oxygens, so I'm going to go 2 times -2 plus my unknown manganese is X. All right, so X plus -4 equals 0, X equals +4. So then I know that this is +4 -2. Those are my oxidation numbers. So that's what I'm doing. I'm taking my easy to assign oxidation number, using that to then calculate those that are not so easy, right? It's because sulfur, carbon, and manganese are not always going to have the same oxidation number. Whereas oxygen and hydrogen almost always do have the same oxidation number. Okay? All right, moving on. Sometimes we have molecular ions, which would be our polyatomic ions. All right? And they're not neutral, right? So rather than setting things equal to 0, we're going to set it equal to the actual charge. So in the sulfate polyatomic ion, right? So here's my two sides, my sulfur side, my oxygen side. They're not going to add up to 0. They're going to add up to this charge right there, which is -2. All right. So again, my easy to assign oxidation number is oxygen. So I've got one sulfur, so I'm going to say X plus 4 times -2. And again, the 4 comes from the subscript. The -2 comes from the fact that oxygen is almost always a -2. And that is going to be equal to that guy, which is a -2. All right. So X plus -8 equals -2. X would be plus 6. So my oxidation number for sulfur in this molecule is plus 6. So this would be a plus 6, right? Oxygen would be a -2. All right. Now, you guys will get better at this, and you may not have to write it out as an algebra problem all the time. I'm just doing this to illustrate. Okay. All right. So here I have a permanganate. Okay. And in this case, I've got manganese and oxygen again. Okay. With 4 oxygens and a -1 overall charge. Right. So manganese is my X plus 4 times -2 equals a -1. All right. So this would be X plus -8 equals -1. X equals plus 7. Boom. Right? So manganese plus 7, oxygen -2, like it always is. All right? Next one, we'll do a slightly more complicated one, which would be bisulfate. Okay? So we got sulfur and oxygen. Now notice that this time our positive one, our positive oxidation number also has a subscript. Okay, so we're going to change my formula up. Again, it's going to be equal to a -2 because we have that charge associated there. All right, I have 2 sulfurs, so rather than just saying X plus, I'm going to say 2X plus 8 times -2 equals a -2. All right, so 2X equals -16. Oops, excuse me. 2X plus -16 equals a -2. 2x equals 14, x equals plus 7. Boom. All right. So my sulfur has an oxidation number of plus 7. My oxygen, -2. There's my oxidation numbers. All right. And that's the gist of how we do this. Okay. We take our easy to assign oxidation numbers. We use those to calculate those that are not so easy. All right, and we set our variables equal to whatever the charge of our molecule is. If it's neutral, we set it equal to 0. If it has a charge, we set it equal to charge. All right. Now, why are we going through this whole headache of assigning oxidation numbers? We've already written our reaction out. Let's say we've already balanced it. We've already labeled aqueous and solid. We've already determined whether there's a reaction or not. We've even eliminated spectator ions at this point. Why are we going through this whole effort of assigning oxidation numbers? That's because in oxidation or redox reactions, there's a transfer of electrons occurring, okay, unlike non-redox reactions. All right, and part of what you need to be able to do to be fully informed is map out the transfer of electrons, and that often involves some release of energy. Okay, and we'll get to that more later. But for a full understanding of oxidation and reduction, we have to be able to take our oxidation numbers and use that to figure out the transfer of electrons. So oxidation and reduction, okay, or redox just means we're transferring electrons from something to something else. Okay, so there's an acronym or a mnemonic that I would like you guys to remember, and that's OIL-RIG. OIL stands for oxidation is loss, RIG, reduction is gain. All right, so there's a substance that gets oxidized, and there's a substance that gets reduced in redox reactions. The one that is oxidized loses electrons from the left to the right. The one that is reduced gains those electrons. All right, and we have to use our oxidation numbers to figure out what loses and what gains. Okay, I will show you guys how to do that later. Okay, but that is the ultimate purpose. All right, so when you guys come to class, I would like for you to know what I'm talking about. When I say oil rig, this should be in your notes. So you should understand that whatever is being oxidized loses electrons. Whatever is being reduced gains electrons. Okay? Kind of like we learned in our acid bases, where the acid loses a hydrogen, the base gains a hydrogen. In this case, oxidized means losing electrons. Reduced means gaining electrons. All right? So let's just take one example. I know this lecture is getting past that 15-minute mark that I like to keep myself to, but this is a fairly complex concept, so you're going to have to shine it on for another minute or two. All right? So let's do oxidation numbers on this guy. So I got manganese solid, right? Manganese is a transition metal. Okay? But on this side of the equation, notice that it's solid. That is elemental, folks. What are all elemental oxidation numbers? 0. All right. Now here I have lead nitrate in its aqueous form. Okay. Now I could split this up into ions, but right now I'm just going to label oxidation numbers. Now here I'm going to infer oxidation numbers. So I know that nitrate, this whole thing is a -1, by the way. I've got 2 of those. So that means my lead's a +2. All right. My nitrate looks the same on both sides. Now, sometimes you have to get the oxidation number for the nitrogen and oxygen. All right. In this case, because nitrate stays intact on both sides, you don't necessarily have to. All right. So I could just say my nitrate's oxidation number is -1. Okay. And -1 there. Okay. Now, my manganese on the right-hand side, okay, here it is not elemental, so its oxidation number changed. That tells me this is, by the way, a redox reaction because there's a change in oxidation number. I've got 4 nitrates, okay, so this is an ionic compound, so it's going to be equal to 0. So I'm going to take x plus 4 times -1 equals 0. X plus -4 equals 0, x equals 4. So manganese is a +4. That's a -1, +4, -1, +2. All right. This is elemental lead, right? So that's a 0. And there's my oxidation numbers. Okay. So what we're eventually doing, okay, with this is we're identifying where the electron transfer occurred. Now you'll notice that the nitrate here, the oxidation number stays the same. That also tells me that might be a spectator ion, right? And if we did this in the net ionic form, which we will do down the road, okay, I would get to cross that nitrate off. And so what happens is the electron transfer occurred between manganese and lead, right? So in this case, a manganese donated 4 electrons to become a +4. And we'll talk about how I know that's 4 electrons later. I just wanted to introduce what's happening during a redox reaction. There's a transfer of electrons. Okay? And we recognize a transfer of electrons when the oxidation number changes from one side to the other. Manganese from a 0 to a +4. In order to do that, they had to get rid of 4 electrons, right? The leads, okay, this is not balanced, by the way. Shame on me. 2 there, 2 there. Holy cow, Mr. Huderberg. Right? The 4 electrons went to the 2 lead ions to make them neutral, is essentially what happened. Okay? But that and more later. All right? Right now, you need to be able to walk in the door tomorrow feeling a little more confident in your ability to assign oxidation numbers to all the atoms in a written out chemical reaction. Okay? Peace.